Happy birthday, laser. Thank you, Theodore Mayman, for your invention that changed the world. Welcome, everyone. We're happy to celebrate this special occasion, the 60th birthday of the laser, together with you. We, that is a cooperation of the PR department of the Max Planck Institute of Quantum Optics, the PR department of MCQST, which is the Munich Center of Quantum Science and Technology, and the Photon Lab, which is a student lab where classes from different schools in Germany come and they do experiments with quantum technologies. This celebration is a bit different than we had planned, but that doesn't surprise anyone anymore, right? The corona pandemic created new challenges, and instead of a day of open doors at the MPQ, we try new things, we learn, and we celebrate with you still, just digitally. Challenges are a part of life, and Theodore Mayman, the father of the laser, could tell you a thing or two about challenges. His boss was not really sure that the laser would be worth to invent and to start with it. And so Theodore Mayman fought for it. He got some money by his boss, but it was really not a lot of money. But still, he got the laser working. The first laser actually started working on the 16th of May, 1960, today exactly 60 years ago. Yes, and then he wanted to publish his results, but nobody wanted to publish him. Theodore Mayman had really a lot of challenges to face. And in the end, imagine, another person even got the Nobel Prize for the laser. It was a theoretician. So nobody really gave him the praise that he probably should have gotten. During the last week, we had a live lab tour at our institute, and a young scientist, Kayhan, I found that quite interesting. He thanked Theodore Mayman, and that basically is something that we want to do as well today, because it was Theodore Mayman who got the first laser running, and it was his hard work that made it possible. So thank you, Theodore Mayman, for your hard work, for your stamina, and for your ideas. Thank you for the laser. In the course of the last week, I called our times quite often the era of the laser. It has become a crucial part of everyday life. We use it to measure distances for communication, in medical diagnosis and in treatment, and especially in science, like at the Max Planck Institute of Quantum Optics. At our institute, the laser is an integral part of almost all research conducted. During the next 3 hours, you have a chance to listen to three talks by some pioneers of quantum physics, all in important roles in our institute. These pioneers of quantum physics have an understanding of the microcosm or quantum cosm that not many share. So please feel free to ask questions. This is a unique chance to get some good answers. You can write them down in the chat right next to this live YouTube streaming. And Sebastian Platt is going to collect your questions, and he is going to pass them over to our speaker, our first speaker, Immanuel Bloch. But now I give the floor to Tatjana Wilk, who will introduce you to this first speaker, Immanuel Bloch.
So thank you very much, Miriam, for this kind introduction. It is my great pleasure to introduce to you Professor Immanuel Bloch, who is Scientific Director at the Max Planck Institute of Quantum Optics in Garching, and who is also Professor for Experimental Physics at the Ludwig Maximilians University of Munich. Immanuel studied physics at the University of Bonn, and after a research stay at Stanford University, he obtained his PhD in physics from LMU in the year 2000. Already in 2003, so only 3 years later, he was appointed full professor at the University of Mainz. In 2009, he returned then to Munich, where his research focus now lies on the investigation of quantum many-body systems, quantum simulations, and quantum information processing. Immanuel is one of the leading scientists worldwide in the field of quantum simulations. Actually, one of his scientific achievements, the first experimental realization of a quantum phase transition from superfluid to a Mott insulator with ultra-cold atoms, marks the starting point of the experimental research field of quantum simulations. The importance of Immanuel Bloch's work is also apparent when looking at the impressive long list of prizes he got. Among them are, for example, the Gottfried Wilhelm Leibniz Prize of the German Science Foundation, DFG, the German National Merit Medal in 2005, the Senior Prize for Fundamental Aspects of Quantum Electronics and Optics of the European Physical Society, and the Harvey Prize of Technia. Another prize I would like to mention there is the Prize for Excellence Teaching in Bavaria. So, which shows you that you can really look forward to the presentation of Immanuel. And moreover, it shows that he's not only an excellent scientist, but as well a great teacher and mentor. Many of the young academics who worked with him received professorships or permanent positions in research. So, and he's also very active in organizing research. So he is one of the speakers of our cluster of excellence here in Munich, the Munich Center for Quantum Science and Technology. So with this, I would like to pass on now to Immanuel and give him now the stage for his presentation. Thank you.
Okay, thanks a lot, Tatjana and Miriam, for the wonderful introduction. It's a great pleasure for me to join in these celebrations of 60 years invention of the laser. And as you'll see in my talk, actually the laser plays a fundamental role in my own research, and everything we are doing would not be possible without lasers. Actually, already in my first slide, a picture from the lab, you already see so much light being produced by lasers that you can already guess that it really is something really important for us. So I want to tell you a little bit about our research on quantum simulators, realizing Richard Feynman's dream. It's actually very connected to what Ignacio will tell you on quantum computers after my talk. So actually these two talks probably go very much hand in hand. So let's get started, everybody. Okay, so I want to tell you a little bit first about why we're doing what we're doing, why it's so hard to the problems we're studying, and the new methods we're employing to actually solve these, how we use ultra-cold quantum matter to do that, and how we kind of use new exciting techniques to visualize, to take photos of these systems and really give us very visual impressions of the physics that's going on in these systems, all depending on lasers, all happening with lasers all the time. Okay, so what are we trying to do? So basically, I always say what we're trying to do is try to determine the social behavior of particles, many particles, when they come together. So in quantum mechanics, we know the laws by which these particles interact very well, but what we don't know very often is kind of what kind of emergent properties do these particles get when they interact together. So it's like, you know, put a bunch of people together in a room, you know a little bit the social rules by which they interact, but you never know what the outcome of 100 people coming together is going to be. And this same thing we want to do for quantum many-body systems. That's what we call these systems, many particle systems that behave according to the laws of quantum mechanics. And these systems are not only a scientific curiosity, they actually play an important role in many, many important technological phenomena, such as superconductivity, magnetism, novel sensors, or the new field, in this new field of quantum technologies, which tries to build new sensors based on quantum. So why are these many body systems, quantum many body systems, so difficult to solve? And for that, let's quickly take a look at a classical system. Let's say you would have the ultimate hard drive in your system, where you would have each bit of information encoded in an atom, and this atom can be just like a little magnet, and this magnet can point in two directions, up or down, and this up or down direction of the magnet represents a bit 0 or bit 1 in your system. So for example, in the slide you see, all the bits would be in 0 and the magnets all point in the upward direction. And they can point all in the down direction, and maybe then you have some information stored on your hard drive, where then the information is encoded in this bit string of 0s and 1s on your hard drive. Now, the challenge in quantum systems is that in contrast to classical systems, you can not only be in one of those configurations, either one of those configurations, but you can actually be simultaneously in all of those different configurations of the system. So we call this the quantum state of this many-body system. And in quantum physics, we like to use this symbol you see on the left, this psi, Greek symbol, this letter which describes this state. And this state can be in a superposition, as we say, simultaneously in all of the different configurations that we have present in the system. And actually, how many of those configurations are there? Well, it turns out for n of those magnets, spins or atoms pointing up and down, you actually have 2 to the n configurations, which is a really huge number, which you can try for yourself, even for modestly small n. So we say this grows exponentially with the number of particles. So you really have a huge number of configurations that you have to take into account. And that actually means that even for small system sizes with only, let's say, 40 of those magnets, spins, quantum magnets, you would already run in the memory limit of what you could store actually on some of our best supercomputers. Just as an example, I take here this IBM Summit machine. So very quickly, you even run out of memory space, and you haven't done any calculation yet. So you've just tried to store that state. And if you want to just add one particle more, you actually have to double the amount of memory in your system. So if you would want to, for example, do that with 300 magnets, store the states of those 300 magnets, that's still a small system compared to the many, many electrons and atoms we have in real solids. You would actually need 2 to the 300 number of configurations, and that would exceed the number of protons we envisage to be in the entire universe today. So clearly, it's not feasible to go down this route. So actually, I should be a bit careful when I say these problems are unsolvable. They are solvable by using clever approximation techniques, where we basically try to work any small configuration space, reduced configuration space that captures the essential physics of the system, which is down here on the left. But very often, actually, we do encounter situations where we have to explore this entire configuration space, which in physics we call the Hilbert space of the system. And then, of course, this exponential complexity actually hits us. So in order to circumvent this problem, actually, there have been innovative ideas using quantum physics itself, trying to build quantum mechanical systems out of elementary quantum particles like atoms, ions, photons, or solid state devices, to actually build up such artificial quantum many-body systems to actually solve those quantum problems we're interested in. And now there's this whole array of experiments going on in the world, building quantum computers or quantum simulators. Actually, they're very, very interconnected, as you'll see, and trying to build such devices that can tackle such computationally hard problems that we can't tackle on classical computers anymore. And for example, we have ion traps, we have atoms in light crystals, or we have these superconducting devices that people use to build such systems in very, very different kind of configurations. So how does this help us to, for example, in our situation, what I want to show you is how can we gain better access to what's going on in a microscopic solid? Actually, the microscopic solid you see here on the left is this tiny object, this tiny thing that's hard even to see. And in order to look into that real material, you have to build a really good microscope. And that's, for example, what people do in the new X-ray laser sources built, for example, in Hamburg or in Stanford, that can look into real materials with really high resolution. But we actually take a drastically different approach. We say, well, if it's so hard to look into this small material, why don't we just make everything bigger, 10,000 times bigger, so we have a much easier time to look into this system, actually. And that's, of course, something you cannot do in a real material. You can't just stretch and pull from all sides to make it just bigger, because it will just break, as you know. But actually, we can build artificial quantum systems where we can indeed make the system much bigger, where the separations between the particles now is not anymore in the angstrom regime, but is basically 10,000 times larger, and now becomes accessible in the micrometer regime, becomes accessible for us to look into these systems with optical means, with good optical microscopes. We can then look into these systems and make photos of these artificial quantum systems. So just to give you an idea, so we can then basically simulate the behavior of real materials, which actually happens at 10 orders of magnitude higher densities with these quantum simulators. But there's, of course, a price to pay. There's always a price to pay. And the price we have to pay here is actually that in order to achieve these regimes where these kind of enlarged systems behave like these real materials is actually we have to go to very, very, very low temperatures. A billionth of a degree Kelvin, a billionth of a Kelvin above absolute zero is where we basically have to work. So extremely low temperatures, very close to absolute zero at minus 273 degrees Celsius. And there's a quantum mechanical reason for that, which I don't want to discuss for now, but this is basically what we have, what's the challenge in the experiment. And then we can build this quantum simulator in the following way. We can have a certain model, which the theoreticians give to us, and which basically describe how these particles interact with each other. And then we program our quantum simulator to implement this model. We let this quantum simulator run. We measure the outcome. I'll show you in a second how that works. And then from these measurement results, from what we learn, we can then feed back to real material systems in the end. So that's basically the loop of feedback that we do to do that. And what's also exciting actually with this kind of approach is you can also build systems which really have not been found yet, have no existence yet in real materials. So you can actually let your fantasy run wild and discover and realize models that basically have not been found in real materials yet, and which might be difficult or challenging to realize, and you can study already what kind of properties these systems would have. Okay, let me give you a glimpse into what kind of platforms, at least in the optical physics, atomic and molecular physics regime, people are using to realize such systems, quantum simulators and computers. There's on the one hand the so-called ion traps. So these are atoms where you remove one electron. Now the atom has become charged because you removed one electron. It's positively charged. And you can basically trap these ions in electromagnetic cages, as you can see up here. This is a picture from Rainer Blatt's group in Innsbruck, where this electromagnetic cage allows you to create trapping potentials in which these ions can be stored. And here you can actually see a string of 51 ions lined up like on a pearl chain in the system. And now you can go in with lasers and address individual ions. They are like magnets, like the magnets I told you before. You can flip the magnets. You can study what happens when you flip one magnet, how that perturbation propagates. You can have different magnets interact with each other over a distance. So all these things are possible in this ion quantum simulator, ion trap quantum simulator. Then there are the so-called Redburg atoms, which people trap in microscopic focused laser beams. These are like called tweezers, optical tweezers. I'll show you the principle of those in a second in the video. So you basically just focus a laser beam, and in the focus of this laser beam, you can actually trap a single individual atom. And you can make those atoms light up, and then you can see them like in this picture here, where our colleagues in Paris wrote this letter, Pasquans, the logo of one of our research collaborations. And each spot that you can see here is actually an individual atom, single atom, trapped in the focus of these laser beams. And what's really nice, actually our colleagues can also do three-dimensional structures. So just out of fun, they made the Eiffel Tower out of, I don't know, 30 or something, 40 individual atoms in 3 dimensions. And if you go to their webpage, you can actually rotate it and see in 3D how these individual atoms are arranged. The approach we use is actually slightly different, and you actually can have, I think this video is actually how this picture was created. It's also on our MPQ website. It's from Ted Henge. It's basically we use optical interference to create also light potentials, light patterns, and these light patterns allow us to trap atoms. So it turns out that if you take 5 laser beams in this configuration, you send them through these holes, these 5 laser beams, and you take a lens, you put a lens after these holes, and you focus those laser beams. And then you find that when these laser beams overlap and you get interference between those laser beams, you get this beautiful pattern of light emerging. So this is a wonderful picture showing how light interference creates these very regular structures. And these potential, these intensities, this light and dark alternating regions in space, we can actually use to trap atoms. So this light field generates very feeble, very gentle potentials, like an egg cartoon, I always say, for our atoms, but just made out of light, not out of any matter. And the atoms can be stored in these light potentials, and we can study their behavior. The nice thing, of course, of this approach is that you can by change the crystal geometry by just interfering the laser beams under different angles and directions, and immediately you have a new crystal. So you don't have to go to the lab and synthesize the new crystal. You just put your laser beams under different directions, and immediately you have your new crystal. Actually, and we can do this with about a few thousand particles in the lab. And if you want to have more insight on how this was done, actually TED also has his own YouTube channel, Super Laser 123, where you can go and have a look how this actually has been done. Okay, let me show you a picture actually of these lattices and how one can trap particles in them. So in this experiment from TED, he took basically 4 laser beams and overlapped them. And now we're going to look at the pattern that emerges when you overlap those beams. And you actually see for 2 beams, you get like this bright and dark stripes. We call this a 2 double slit interference pattern. When you have 4 beams, you get this more square pattern-like shape. And the fact that this is moving so much is basically due to the fact that these lasers have not been stabilized relative to each other very well. Now we put small plastic particles, small plastic beads in water. They just move around. And actually what's exciting to see is when you turn on the light, can you see how these plastic beads want to follow the light? Okay, so the light really for them is a force, is a potential. In 2D, they want to lock into the positions where the maxima is. And this illustrates how light creates trapping potentials for these plastic particles. And in our case, we don't do this with plastic particles. We do this with individual atoms. But the principle, of course, is exactly the same that I showed you. Now, let me show you how we take some photos of such systems and such many atoms in such light crystals. And I told you in quantum physics, we call this state of matter, describing those systems by this wave function psi. And I also told you that in quantum physics, the strange thing is that you can be in many configurations simultaneously, which we write like this. So we're in this configuration and in this configuration and in this configuration and so forth. But again, the amazing thing in quantum physics is when you go and look, if you would take a photo of this system, and this is what we do, you basically only find one of those configurations actually in the experiment. So only one of them pops up, and you cannot tell which one you will see. We can only predict in quantum mechanics with what probability we will see different kind of those configurations. That's a fundamental principle of quantum mechanics. So basically, when we want to characterize such a system, we take a photo, we get this outcome, for example. Then we have to go in the lab and recreate this psi where we had the plus, plus, plus of the different configurations. And we take another photo. Then in the next shot, maybe we get this configuration. And then we have to make psi again. And in the next shot, we get this. And like that, we can probe how often we get these different configurations. And this gives us a lot of information how these systems actually behave on a microscopic level. So here are real pictures of how this works. So here's this light microscope, a very good objective that we can use to look into this system here. It's a single 2-dimensional system, a plane in which these atoms have been trapped in these light crystals. And when we turn on light to see the atoms, they basically start to fluoresce. It's like a small light bulb turning on. So each atom is like a light bulb turning on. When we turn on the laser light on them, and they start to fluoresce. And this fluorescence we can capture with a microscope and observe then the pattern of the atoms. And here you can see photos actually of these individual atoms trapped in these lattices. So each bright spot that you can see here is actually a single atom trapped in those lattices. And we can also actually manipulate atoms. So we can also go in the reverse direction and focus a laser beam onto the atoms and pattern them and move them around like we want. And for example, here we made them in a psi. Well, you know, quantum physicists by now, they like the psi. So we made a psi out of 26 individual atoms in these systems where we can arrange them. So then you can take photos like this one, where you basically now take a full photograph of the system. You see each of those atoms. When it's red, it means this magnet is pointing up. When it's blue, the magnet is pointing down. And when there's a hole, then there's no particle here, or when there are 2 particles on a certain side, we can also see that. And so basically we collect many of these snapshots, these single shots, to basically gain information about the behavior of the system really at a truly microscopic level. So we really know what all those particles are doing together. So it's like in a real material, if you could do these type of experiments, it's like you would take a photo and you would really see all of the electrons simultaneously in the system. So in order to take this approach a bit further, we want to add a little bit element of programmability. We want to shape the potentials. We want to control those potentials, the lattice structures in which the atoms interact. I already told you we can do that by interfering the laser beams under different angles, for example. But we can also do it by taking these so-called digital mirror devices. This is actually just an array of millions of small kind of mirrors that can be tilted, tipped or tilted to be turned on and off like pixels. It's actually in many of the modern projectors that are used, you have such devices. And we can use that to create arbitrary light patterns. And here are just some images, a line of light, a different crystal structure here, or here are two boxes connected by a very, very, very thin wire of light. So now you can study, for example, you can fill up this box with atoms. This box is empty, the upper right one. And then you can study how the atoms flow through this very thin wire of light from the full box into the empty box, and study, for example, how conductance in wires is depending on interactions, disorder effects, and so forth. You can make box potentials. So really, you can create any kind of potential you want and study how these atoms behave in these different configurations, mimicking the behavior of electrons, for example, in a solid. So actually, in the world of atomic and molecular and optical physics, we have a lot of different possibilities to make those atoms or molecules interact with each other. So on the one hand, we can just have them bang into each other. That's what we call the collisional interactions. Then if they are small magnets, then, you know, basically two magnets, when you put them next to each other, they repel each other. When you put them on top of each other, they attract each other. So you can have longer ranged magnetic so-called dipolar forces. We can also create these strange atoms, these so-called Redburg atoms, where you take an electron and move it to a very, very large radius inside an atom. So you blow up the atom, make it really huge. And then this blown up atom, this really huge atom, can interact with another huge atom next by. Or you can put these atoms between two mirrors and have light bouncing back and forth between those mirrors, laser light, of course. Everything is laser light here. And then this light will interact, that passes through this atom, interacts with this atom, then interacts with this one, and on the return path interact with the atoms again. And like that, you can make all of the atoms interact with each other in such a so-called cavity setup in the system. So there's a huge amount of possibility to engineer and control the interactions in these systems on top of the geometry of the crystals that we have. So all of these experiments have to be done, I told you, at nanokelvin temperatures, which is like really, really cold. But if you come into our labs, you might be amazed to see that we don't use any cryogenics or something. You don't find any liquid nitrogen or helium. There's no refrigerator. We just use laser cooling, tools of laser cooling to cool down the atoms. And once they're so cold, we have to basically isolate them from the environment. And in order to do that, we just use a very, very good vacuum vessel. It's just like your cup of coffee or tea that you mug, you all know, your thermos cup of coffee, thermos cup is the same principle, just much better. And like that, we can trap atoms in these evacuated vessels behind this wall, this glass wall. We have this nanokelvin temperature, but the glass cell itself is at room temperature. And we just hold the atoms by either magnetic forces created by the current running through these wires, or these optical crystals that I showed you before, where we shine in lasers from different directions through this glass cell onto the atoms. So here's a picture into the lab. If you maybe had a chance to watch Tony's live lab tour on Instagram, you will have seen the lab live already. Here it shows you a picture of how it actually looks. So we have a lot of these lasers. So you can now totally believe me that we rely on Maimann's invention. So here are all the lasers. Here on the left-hand side is the actual experiment, and we connect the two tables with these yellow cables, these optical fibers, which allow us to guide the light from this laser table over to the experimental table and do the experiments that I talked about over here in the vacuum vessels. Everything is computer controlled in the end. So once everything is aligned, our students and postdocs, they go and program the system. They just write here, as you can see, a certain code, how the system should be programmed and controlled, and then run that overnight, for example, and get the measurement results on the next day, and then basically read out this quantum simulator the next day and analyze the results that you got. So it's pretty automatized by now. And of course, we hope to make it also eventually into a system that you can access maybe yourself remotely at some point in time to learn about the quantum physics of these particles yourself. So what kind of physics can you study with these systems? Well, I told you already, they are great systems for studying material science, condensed matter physics, but they actually also turns out great systems to study high energy physics phenomena, as we showed in one experiment, where you might have heard about the Higgs particle in high energy physics, one of the and most fantastic kind of discoveries this decade in high energy physics. And actually a very related Higgs particle in a different incarnation actually also occurs at the lowest energy scales. So typically Higgs particle you associate with the highest energy scales we access in accelerators. But this actually also is a phenomena that can occur at very, very low energy scales. And we probed that, for example, in these systems, and kind of could resolve the controversy in these systems. You can also, because these systems are not connected, are totally isolated quantum systems, you can also realize funny states of matter, like these negative absolute temperature states. I already told you that we're working at extremely low temperatures, and now I'm telling you we can even work at negative absolute temperature. And you might wonder what's that, and I don't have the time to talk about it. But actually, if you want to learn about it, I recommend to you this YouTube channel from our colleagues in Nottingham University, 60 Symbols, where they had a really nice kind of video explaining what these negative temperatures are about. And actually, I think by now it has over 1 million views. So just go there and have a look for yourself how this works. I just want to show maybe at the end a kind of a simple example of how these atoms behave. And I call this the quantum horse race, where we line up the atoms along a line. And then we make them, actually, we make the lanes, we separate the lanes between the atoms. We make the barriers between the lanes very high, so they can only run from left to right, basically in the horizontal direction. And then we can start our quantum horse race. We can let them, we can let them run and evolve. And then at the end, we can take a photo. And now what's misleading in this animation is that it suggests that we know which particle is the fastest all the time. But in quantum mechanics, we don't, before we have not made a measurement. Only when we make a measurement do we know which one's leading the race. And so here are some examples of that. So we line the atoms up in this diagonal direction. We let them run. And then after a certain time, we find, for example, this one is the fastest one. This one has moved the fastest in this particular race. And then when we repeat the race many, many, many times, we can we can measure the probability of finding particles at a certain distance. And that's something we can compare with quantum mechanics. And as you can see here, it agrees wonderfully with quantum mechanics. Here's another example where we show this probability distribution. The measured one is this histogram. The orange curve is basically what we measure in the experiment. What quantum mechanics theory predicts, and you see they agree extremely well. I think my time's running out, so I will skip this example. It's just a more complex example of doing really some fancy state-of-the-art quantum simulation, really helping us to understand real materials. The final point I would like to make maybe is that this research that we're conducting is not only useful for quantum simulations, but in fact, it also is used to realize the best clocks that we have in the world. So clocks are important because they are, for example, on all our GPS, all our navigation systems rely on having good clocks around us. Actually, in each of the GPS, GLONASS or Galileo satellites flying around us, you have atomic clocks that send timing signals to the Earth. And from these timing signals, you can determine your position in space. And having more precise timing allows you to do better position determination. And so clocks basically are two things. They are something that is oscillating periodically, like a pendulum in the medieval days. People use pendula. And then something that counts the number of oscillations. And that's actually how we define the second. After a certain number of oscillations of this pendulum, in our case, an atomic pendulum, we say that's 1 second. That's just how we defined it. Okay, that's how the second is actually defined. And it turns out you can make the best clocks today by putting such atoms in optical lattices, making their electron clouds start to oscillate. So this is the pendulum, basically. And because they are so separated on the lattice sides and they don't collide with each other, you can make them oscillate for very, very long times and count this clock over very, very long periods and make very, very precise clocks. And it turns out actually that these clocks are so good that if we would have started one of them, for example, 13.8 billion years ago at the start of our universe, today it only would be 1 second off. Okay, that's the precision of these atomic clocks. So it's really mind-boggling what you can do also in science and technology with these trapped atoms in these optical lattices. Okay, with that, I want to finish, and I just hope you gave you a brief glimpse into our research field, into the world of quantum simulations, in our case with atoms and lattices. There are many applications in science. We are looking if we can also find applications for industrial needs and trying to see how we can employ these quantum simulators in the future. For sure, they're super exciting as a scientist to be able to see these atoms individually. That's a lot of fun and is really exciting for everybody involved in our research teams. Yeah, with that, I thank you all for your attention. Happy to take your questions. And yeah, so I'll leave you with this nice picture of Munich and all the MCQST and MPQ team organizing this event. Thanks a lot.
Oh, thanks, Immanuel. And we already have a question on the YouTube live chat. And so Rishikesh Dixit asks how you can actually manage and create the potentials at the atomic level so that the atoms get trapped using lasers. So how do you create these lattices?
Well, so basically it's actually very simple. You just have to overlap laser beams. So actually this pattern that you see here, that emerged here, this light pattern, actually you just realize by overlapping, in this case, 5 laser beams. If you overlap 2 laser beams, you know, if you think of the lasers, the light as just waves, electromagnetic waves, but think of it like water waves for now. And if you have one water wave and you overlap with another water wave, whenever there's a maximum coming together with a maximum, then they will enhance and force each other, so the wave will become stronger. But if a wave maximum hits a wave minimum, then they can actually cancel out and there will be flat water, so to say. And that's what we see here in the phenomena of light. So where we have bright regions in space, that's where the light, the electromagnetic wave, interferes constructively. Where there are dark regions in space is where the light interferes destructively. Actually, there's a very practical example of this interference also that you know from your, maybe if you have noise canceling headphones, for sure you know about them. They work in the same way. So they basically try to find out what's the ambient sound, and they try to create a destructive interference of this ambient sound by creating just the right sound wave that cancels out at the position of your ear, so you don't hear anything at the position of your ear from the ambient sound that you want to cancel.
Okay, there's also questions about temperature. Maybe let's start this off. So it seems very strange, right, that you can create your artificial materials, and we all know that if you put a block of something in sunshine or thermal radiation, that it heats up. And you're saying you're at these crazy low temperatures. How does that even work? And then related to that, the negative temperatures, which are a different, slightly different thing. So how is it maybe possible to use your research? This is a question from Ziad Shehata, to also create negative temperatures in the internal degrees of freedom of a molecule.
Well, maybe let's start out with the first question, right? So why don't these lasers heat up? I mean, that's, of course, every one of you, probably when you think about lasers, you don't think of cold temperatures, you actually think of the opposite. Somebody welding, laser welding, machining, cutting, Star Wars, whatever. So something, you know, really violent. And that, of course, depends, as we see here. I mean, basically, first of all, one special thing about the atoms is that they don't absorb the light so much. They just basically absorb a photon, but re-emit it again. And basically, in a way that doesn't make them heat up. Yeah. So we try to keep this absorption process of the laser very low, but there are still other effects of the laser that remain that allow us to trap these atoms, for example, as you can see here. And this actually gets more difficult if you have a more complex object like a big molecule. And to do these kind of, because already the big molecule would kind of absorb radiation from the background thermal radiation. And in order to do such experiments with big molecules, you would actually have to go into a cryogenic environment to basically reduce the black body background in the system. Yeah. So here we basically use more the effect that the atoms don't absorb the light. They more act like small glass beads, and we use more the refraction that you have. So think of, a lens. You can send a very powerful laser beam through a lens, a glass, it will not heat up the glass, right? Or very, very low, but it will do something to the light. I mean, the light does something to the glass, is affected by the glass, and vice versa. And that's actually what we make use of here. So we're making use more of the so-called dispersive effects, the refractive effects that can occur when light interacts with matter, rather than the absorptive effects where, really that would lead to strong heating up of the atom.
Okay, well, thank you very much. There's another question about quantum computation. So let me paraphrase this a bit. Question by Felix Zilk. We're going to hear another talk on quantum computation in a few minutes. And you were speaking a lot about quantum simulation. Can you maybe elaborate a bit on the difference between the two? So you're saying they're both useful for calculating things, but in what way?
Yeah, so I can just basically try to have this slide where it basically tries to illustrate the difference and the similarities. I just skipped it for the purposes of this talk. So basically in the both approaches, your goal is the same thing. I mean, you want to solve a certain complex problem, many-body problem, like from material science that I talked about. And you can do that in two ways. So you basically want to study how does the system, remember that's the psi we write down, how does it, for example, change after a certain period in time. This is why we call this psi of t. So this is the state at this later time t. This is the state at the initial time 0. And then you have to basically let it run, evolve it with this very complex many-body Hamiltonian, and that's the difficult thing. So you can do that in two things. In the analog approach, this is the quantum simulation approach, you try to program your system to directly implement this so-called Hamiltonian, the laws by which the particles interact, and then you just let the system run. In a digital quantum computing based approach, you try to you don't have maybe access to this Hamiltonian directly, but you try to build it up through discrete operations. You try to mimic the behavior of this kind of complex many-body system through discrete operations that in the end should give you the same result. The advantage is here that basically with a few elementary gate operations you can mimic, you can build up any Hamiltonian, any kind of system you can build up based on just a very few gates. The challenge is what makes this approach difficult, the digital approach, is that you need many, many of those gates. You might need millions of those gates and millions of particles to do that, to really have a universal approach. And we don't have that yet. And it's very challenging to reach that. We don't know if we will reach it. Hopefully we will. But as long as we can't, we might just rely on the other approach, which is not universal, but already today can give us answers to some problems which are very, very difficult to solve.
Well, thank you very much. This leads me into my next question. So this is maybe again paraphrasing a bit, a question by Majid Zahedian on applications. So you said that this is useful for something. Clearly you're working on fundamental research, but what do you think could quantum simulation be useful for? And then Majid's question was also about quantum sensors. So in what way can your research be applied, do you think, in the near or far future?
Well, for the applications, I mean, one phenomena I didn't have much time to talk about that's really of interest to us, which we like to study, is this so-called problem of high TC superconductivity. So superconductivity is phenomena when you basically cool down a metal, for example, or some compound, and it loses resistivity. It can conduct current without resistance. And of course, that's a huge thing, right? I mean, you can all the power losses you have on cables, all the energy that's wasted, that's a huge thing if you could understand that and build that at room temperatures. So we don't really know how these high TC, high temperature superconductors work, and we would like to understand that better, to engineer them and to our purposes. And so we believe we have some models that should capture the essential physics that's going on, but we can't solve them. They're very simple models to write down, but already when we try to calculate them on a computer, we can't solve them. So that's one thing we're interested in. So that's one thing we're looking at. In terms of sensors, I think this clock is really the very, very good example, because it's already, now working, and it's very clear that in a few years we will change our atomic clocks, our definition of the second, to such systems that I show here, of these atoms trapped in lattices. And better timekeeping, better navigation. Again, just imagine how that could revolutionize construction industry if you can not only determine your position within a meter, but let's say a millimeter, and how everything would be revolutionized if you could have even better navigation purposes. So I think that's a good example for a technological application in metrology, in sensing.
So, and you're saying this really uses quantum mechanics to make the sensing process better in some way?
I think in the end we will. Right now, people are just using these as independent atoms, that basically independent pendula. Each of the atoms is just an independent pendulum, and they don't interact with each other. Actually, you don't want them to interact because they can perturb each other. But my guess is that at some point we actually want to engineer the states of these atoms to have a collective state which is even better suited for these time purposes. And there's where our research also, I think, comes in, trying to engineer such entangled, so-called correlated states of these atoms that could lead to better timekeeping overall. Yes.
Mm-hmm. Okay, great. Thank you very much. And so maybe one final question, which is a bit more broader. So you seem to be very excited about this field of research, clearly. Do you think this, what's your perspective for the future? If for all the high school students or beginning physicists watching this, what do you think where this will go?
Well, that's of course hard to say. I mean, 10 years down the road, I don't make any predictions. I don't even know where we're going to be in 5 years. But I mean, clearly it's a super exciting field, and I've started to work myself in this, about 20 years ago. And this has really been an extremely exciting field, very fast developing, and opening so many new directions, lines of research. In first of all, fundamental science. Just my curiosity started with the curiosity for quantum mechanics, because it was such a strange theory, so counterintuitive. I really enjoyed that a lot, and that led me to this kind of research where we can study quantum mechanics and all these complex many-body phenomena, which are typically very hard to unravel in real materials, and we can study them in these very clean environments by taking pictures. So I think this is going to continue the next 5-10 years. The race to build better quantum simulators, quantum computers, I think has just started, actually. So I think this is really an exciting field of research to get involved in and to learn about.
Mm-hmm. Great. Well, thank you very much. There's also just one more thing, just a question who just came in. There is a question about software. Someone was asking, Rodolphe Masson was asking who was developing the automation software for your quantum simulation lab. Did you do that yourself, or is this some big company that does it?
Well, actually, Sebastian, people like you did it. So behind that is like team members who developed this. So we do that all ourselves. So I think at some point, we'll have to involve more professional people who do that for a living, people from computer science. But for now, we, as experimental physicists, also we like technology stuff, right? We all love that, and we're working in this field. We basically build those systems ourselves. So a lot of the electronics, the hardware, the software, we build ourselves. A lot of stuff we buy, but a lot of stuff is actually done by ourselves. So when you work in one of our labs, you actually get into contact with many different topics, software, hardware, optics, lasers, vacuum. So it's really, and of course, quantum physics. And I think that's what made it so exciting for me to work in this field.
Oh, one more question, actually. Sorry, it keeps coming in by Varun Chandrasekar. This is about maybe an outreach question. So how much contact do we have with other people in the community, in particular this channel that you mentioned, 60 symbols, who were doing these negative temperature explanations? Do you do this often? Is there something you are involved in?
You mean from the outreach part, or from in general in the community? Or, I mean, of course, with the community, we have science community, we have a lot of connections. This 60 symbol people, I think they just did it themselves. We didn't have any prior contact with each other. I just ran into their video about it and thought it was great. They did a great job. I mean, in general, they take complex physics phenomena and try to explain them in very basic ways, simple terms, and they do a great job. So it's a great channel to get informed. But of course, we also try to do outreach events and try to ourselves to do these things.
Okay, I think with that, we're finishing up here. Thank you again, Immanuel, for a great and informative talk. And I'll hand back to our organizers.
Thanks, everybody.
Thank you, Immanuel, and thank you, Sebastian. In case you have not been on our Instagram profile yet, it is @MaxPlanckQuantum. I have some recommendations because we've seen the pictures with the atoms, right? So for our Christmas cards, we actually got a Christmas star and a Christmas tree. So if you go on our Instagram profile, you can see some trapped atoms in lattices, which is quite nice. And we also have the Fresnel interference videos on our Instagram profile that Theodor Hensch made. So if you want to see them, check them out. It's really beautiful to watch when they start dancing and shaping different forms. So before I introduce you to our next speaker, let me tell you a couple of things about this will go on now. We programmed another live stream for each talk. So the next live stream will be at 3 p.m. And it is right next to the one that you were just watching. It is called Ignacio Cirac, Quantum Computers, What, When, and How. And I want to point out that there will be a quiz on Kahoot at 5 p.m. with questions regarding the 3 talks today, as well as the lab tours last week. There's some nice prizes to win, and I'm going to share my screen for a second just to show you what you might win if you are interested. So these pretty cool Corona masks, we thought about, like, I mean, it's Corona and it's the 60th birthday of the laser. So we were like, okay, let's have the lasers win against Corona. But yeah, you can win of those. Some of those, we have 10 for the first 10 places. I am getting one, and everyone who was part of this, and I can't wait to get my own mask. So the thing is, with YouTube, it is a live stream, and we have about a delay of about 30 seconds. So if you want to have a real chance to win one of those masks, you have to leave YouTube. I'm sorry. So you have to come in for Zoom. The link for that is underneath, basically, the last video live stream that you can see on our YouTube channel. There is this tiny URL link, which is called Laser Quiz -English. So please click on that. If you haven't used Zoom yet, I mean, most of us probably have in the current situation, but if you haven't, it is super simple. You have to click on the link, then you have to download Zoom. It's done in a minute. It's not complicated at all, but it gives you a chance actually to win a prize. Because the thing with the quiz on Kahoot is that when the question is asked, you only have a certain time to answer that question. So if you do it on YouTube, you will basically all the time get the result. Sorry, you're too late. So if you really want to partake in the quiz, please join us on Zoom. I know we're all a bit hesitant with new platforms, joining somewhere, but you just have to download it. You don't even have to make an account. You can just use it in your browser. It's super simple, and I promise you the quiz is fun. So that would be really nice if you join us. Yeah, and that is enough for here and now. We see you again in 5 minutes. And then Ignacio Cirac is going to talk about quantum computers and when and how they might be realized. See you then.